All right, in this chapter, we're going to explore what chemistry is. Go dive into what we study when we study chemistry, and then expand backwards a little bit and discuss what it means to do science in general. Like, what is science? Uh, we'll specifically focus in on how to do science, and we'll see that a big part of that is taking measurements. Basically, you'll see that science involves a lot of capturing of data, and quantitative data is what we know as measurements. So we'll basically start off sort of narrow what is chemistry, and then sort of expand outwards and go more and more general. Okay, so what is chemistry? What are we doing in this course? Like, what are we studying here? Well, chemistry is the science of matter. Matter is literally what everything is made of. It's just what we define as stuff. We'll go into more detail into what that actually means in the next chapter, but for now, understand that we're just going to study what stuff, physical stuff is. So we're going to look at composition, what is stuff made of, structure, how the pieces of matter are held together or arranged, the properties of this matter, what kind of characteristics does it have, as well as look at the reactions that matter undergoes. How does matter change? How do substances interact with each other? Um, yeah, and that's essentially what you cover in the study of chemistry. Now, you can do this from multiple angles. There are different ways to approach this. So, in this course, we're going to cover what's called general chemistry, which is really sort of a combination of physical, analytical, and inorganic chemistry. Now, if you go on to take Chem 104, that's the sort of second half of what we call a GOB sequence, or general organic and biochemistry sequence, and that's where we'll cover organic and biochemistry as well. So these five branches of chemistry are the five traditional ways to kind of approach chemistry as a science in general. So physical chemistry, as the name suggests, looks at the physics behind chemistry. We look at interaction between matter, but look at it in terms of things like energy and forces. In analytical chemistry, we try to come up with methods to analyze chemicals, to determine their structure, to determine basically how, what actual molecules are, what they look like, and so on. In inorganic chemistry, to explain inorganic chemistry, I should probably first explain what organic chemistry is. Organic chemistry is the study of carbon-based chemistry. So we look at carbon-containing compounds, and typically it's carbon and hydrogen and a few other elements, but most organic compounds have to have at least carbon to be considered an organic compound. Now, you're probably saying to yourself, wait, there's an entire branch of chemistry that focuses on compounds with just one element? Yeah, carbon is actually very versatile like that. It forms all sorts of compounds, and these compounds are really, really interesting. They have interesting properties, they do interesting reactions, and that's why there's an entire branch of chemistry dedicated to it. Okay. Now, inorganic chemistry is basically the study of everything else in the periodic table, which also sounds kind of weird. But typically, inorganic chemists will focus mostly on things like the transition metals. I think that's where you'll kind of find the bulk of inorganic chemistry kind of focused. My own research background actually is I technically was an inorganic chemist, but I was organometallic. So basically, try to design catalysts to do organic reactions, but these catalysts had metal centers, specifically ruthenium and palladium. Anyway, I'm going off on a tangent here. Let's focus on this on Chem 103 here. With biochemistry, as the name also suggests, this is kind of the biology side of chemistry, or rather the chemistry of biology. So in biochemistry, you look at a lot of biological pathways and biological processes, and you try to understand the chemistry behind those. So, for example, in biology, you try to see, let's say, a mechanism where a particular enzyme's involved, right? With biochemistry, you're focusing on that enzyme. What's its structure? How does it function? What kind of reactions does it catalyze? Things like that. So that's basically, different ways we can approach the science of matter. You can see that this is a very, very broad field. Which is why probably Chem 103 itself is broad, because we kind of have to cover a lot of ground here. So, where does this chemistry happen? Well, because chemistry is the science of matter, and matter is all around us, and matter is literally everything we're surrounded by, chemistry happens pretty much everywhere. There are chemistry reactions that are happening just in natural everyday processes. So anytime you cook food, or you see the leaves changing colors in the fall, or you use your battery on your cell phone, these are all chemical processes that are going on. So this class, while you might not go into every specific process, you will get a general understanding of a lot of these processes and how they work and what's going on. Now, I mentioned that a lot of these chemical processes happen in nature, like I said, with the leaves changing color and things like that. And a good chunk of chemistry involves studying how that works. So, for example, with those biological processes, we biochemists will basically focus on that and understand how those processes happen, right? But that being said, with our understanding of how this works in nature and how these processes work in general, we can then harness that information, we can harness that understanding and make it work for us. So we can take our chemistry knowledge and apply it to completely artificial or man-made scenarios. We can use things that are not organic or not biological and create or run processes that are just solely for the benefit of mankind. So doing things in laboratories or in manufacturing. Okay, so this includes things like, for example, making pharmaceuticals, or just making certain synthetic fibers out of raw materials we get from crude oil, for example. That brings us to the definition of a chemical. Now, when you hear the word chemical, you probably have a mental image of something that's kind of yucky, something that is artificial, that's pretty bad for you, that it's made in a lab. If it gets out into the groundwater, it's going to kill you or make you very sick. And don't get me wrong, there are chemicals that do that kind of stuff, but the term chemical is a lot broader than you think. Remember, chemistry is the science of matter, of literally everything. And so a chemical, which is something that's used in a chemical process, is also very, very broad. It can also include literally everything. So even though, yes, like the chemical, when we think of a chemical, it's things that we find in a lab or in a factory, but really every substance could be considered a chemical. Now, we'll use the broader term substance here to avoid confusion, but my point here is to kind of lose your fear of that word chemical. Just because you see it in a lab doesn't mean that it's not necessarily natural or something that can be used in a natural process. Okay, and I'll go into that distinction a little bit more in a second. Okay, so a substance is any material, any chemical that contains just one piece of matter, one type of matter, same sort of repeating units over and over again. Okay, so we sometimes call that a pure substance to avoid confusion. Again, we'll talk way more about this in the next chapter. That's kind of a good chunk of the next chapter, making that distinction between substances and mixtures and what that all means. Okay. So basically, we can use substances and mixtures, I guess, as well, in all these chemical processes, and these can be defined as chemicals. So you want so even though you might have that mental image of a chemical being something synthetic, that is to say, something that's made in a lab, really, it's a little bit fuzzier than that. The distinction's a little bit looser than you think. So we're going to make a little distinction here between something that's natural versus synthetic, but you have to realize that a chemical can be that same thing. So for example, if you have vitamin C in an orange, vitamin C is what we call ascorbic acid. That's its scientific name. Well, yes, you can extract ascorbic acid from an orange or any citrus fruit, but you can also synthetically make it in a lab from glucose. You can do a couple of reactions to a glucose molecule and turn it into ascorbic acid. Now, is the ascorbic acid that's from vitamin C from an orange any different from the ascorbic acid that we made in a lab? And the answer is no. From a chemical standpoint, they are identical molecules. They will do all the same reactions. They'll have all the same chemical and physical properties, and that's why they're considered the same chemical. What's different is the source from which they're made. Now, you can have arguments over is it better to get your vitamin C from an orange versus from a pill that's made in a lab? You can have arguments over getting it from a natural source includes other, healthy chemicals that are found in oranges. But that doesn't change the fact that the vitamin C itself is identical. Okay, so you've got to be careful of how people frame those kinds of arguments. Okay, another example here would be with alcohol. So when fruit rots, you get ethanol, right? So the sugars in the fruit will start fermenting into ethanol, which is a type of alcohol. Well, you can also make ethanol by reacting ethane, which is a hydrocarbon, is an organic compound, with steam, with water, and it will also make ethanol. Now, ethanol here is the same chemically as the ethanol that you get from fermenting fruit. Now, the fermenting fruit will have a whole bunch of other stuff in there, not just the pure ethanol. And also when you do a lab, or you make ethanol in a lab, you will get other byproducts and stuff that you've got to separate out and purify. But the bottom line is this chemical ethanol is the same as the chemical ethanol that would be made from fermenting fruit. Okay, so again, we've got this distinction between a natural versus a synthetic chemical, but from a chemistry standpoint, they're the same thing. Okay, in fact, with alcohol, with ethanol, we can even add another distinction where we can get naturally derived chemicals, where we can take a natural process or a biological process and artificially control it. So when you brew beer, that's basically taking yeast and they're going to naturally turn grain into the sugars in grain into ethanol, but we're making them do it. So that's why it's a natural process, but we're kind of artificially controlling it. So it's kind of that in between being purely natural and being synthetic. So yeah, so basically my point here is that the word chemicals is a broad term. There's chemicals all around us. So I just wanted you guys to kind of lose that sort of mental image of what you think a chemical is strictly. It's a lot broader than you think it is. Okay, so that being said, let's move on. Let's take a step back and talk about how science is done. We mentioned that chemistry is the science of matter. Well, what is science? How do we carry out science? Science is just an endeavor to gain knowledge, and there are multiple ways to gain knowledge. There's multiple ways to understand how the world works and to help explain how the world works. Science is kind of set apart from other branches of knowledge in the way that it carries itself forward, in the way it organizes its information and obtains its information in the first place. Essentially, the way that science is done is kind of systematic. And this sort of systematic experimentation is what really makes science unique. Okay, so for example, with other endeavors, let's say we're studying history. All right, in history, you're still trying to understand how the world works. You still want to know why a particular event happened. So you learn about facts around a particular period in history, and you can then craft an understanding of what was going on in that time period. Why did these events unfold the way they did? What could have been done differently, and how would that have changed things? Stuff like that, right? Well, if you were to write a history paper where you did that, where you explained a particular phenomenon, you would be doing so from a standpoint of argument. You would take like historical documents, you'd study this material, and you would put forward an argument saying that this, based on this evidence and this evidence, this is what I think happened. Right? So you can see where I'm going with this. It's from a standpoint of argument that you build your knowledge base in a field like history. Science works through what we call a scientific method. We use physical data, we use physical evidence to back up our arguments like in history. But the difference is that the sort of feedback loop that data is passed through, the process through which we generate that data and then verify it, is unique. You don't really run experiments in history, for example. Okay, you don't run experiments in philosophy or in English or anything like that. So how does this work, right? How do we run science? How do we do science? When we do science, we have to start off with what we want to explain, right? We're trying to explain something, we're trying to understand a particular phenomenon. So it starts off with identifying that phenomenon. We observe something happening and we want to understand what it's doing. Like, how is this phenomenon occurring? So the next step is to put forward a hypothesis. A hypothesis is an educated guess. We've observed a particular phenomenon, and we want to know. Well, we want to come up with an explanation for it. So we say, here's what I think is happening. All right. This, like I said, is just an educated guess. Now, it could be a really good educated guess, because let's say you have a lot of experience in that area, you've seen a lot of similar systems, and you've got a good idea of how they work. Your hypothesis might be relatively close to the truth, but again, it's just a guess at this point. A hypothesis by itself is kind of worthless. No matter how confident you are about it, you need to then move on to the next step, which is design an experiment to test that hypothesis. You want an experiment that basically gathers evidence for the hypothesis to help test it, but also to kind of test against it. You want to sort of disprove the null hypothesis, which is that the hypothesis has nothing to do with your system. This, by the way, if you've ever heard of a controlled experiment, this is kind of the purpose of a control, to make sure that that the thing that you're testing in your hypothesis is actually even involved in the experiment. Okay, that by removing it, the phenomenon doesn't still occur anyway. Okay, that sounds really basic, but it is something that's very important. Okay, so you do a bunch of experiments and you get some evidence, you get some data, and you have to analyze this, of course. And now the moment of truth is, what does that analysis tell you, right? Does it tell you that your hypothesis was good or not? Now, it could tell you, well, your hypothesis is wrong. You've got your null hypothesis was proven, you're completely wrong, back to the drawing board. It might tell you that your hypothesis it's kind of getting there, but it doesn't really explain this very well. So you may want to tweak your hypothesis and then design a new experiment and keep going back. All right. So this loop between hypothesis and experiments need not be a one-time loop. You may be going through this quite a few times, trying to tweak that hypothesis and get it to explain that observation more and more fully. Okay? When it gets to the point that the evidence that you're getting from your experiments really explains what's going on in your observations, and when you've tested it so that it basically doesn't prove the null hypothesis in a way, it you've now got what's called a theory or a law, depending on the type of experiment or the type of data you're using. I'll get into that in a second. Okay, so this is the point at which you've kind of made it from a science standpoint. You've added a piece to the knowledge base of science, and at this point you want to kind of share that with people. You want people, other scientists, to peer review that, to kind of also run experiments and kind of provide evidence for that. Now, every now and then you could have evidence come to light from other scientists or even from yourself from future experiments showing that, hey, maybe that hypothesis wasn't perfect. There's something it doesn't explain properly or doesn't explain enough or doesn't even touch. Then you sometimes occasionally have to go back to that hypothesis stage. This usually is, if you ever go on to take a philosophy of science class, and I highly recommend it, it's a really interesting field. This is where you have what are called paradigm shifts or a crisis in science, and they are really interesting times. So, again, it's not, you don't see it as, don't see them too often, but they're very exciting when they do happen. Okay, so let's take a really ordinary, everyday example of the reasoning behind this sort of scientific method, or how we approach a science problem. Now, this is a really silly example, but bear with me. So, let's say you are playing a CD. Now, some of the younger students, a CD is a piece of plastic that used to contain music. You would put it into a CD player, it would spin, and it predated MP3s. Okay, so you play a CD in your CD player, and your CD player, like the song doesn't play properly. It starts skipping. Okay, so you now need to figure out what's going on, right? Why am I not getting good music out of my CD player? So you come up with a possible explanation. Your first hypothesis is that your CD player is broken. Something's gone wrong with your CD player. And so you need to determine, is that the case? Do I need to buy a new CD player? That's really expensive. I should probably first figure out if that's the reason why my music's not working. So let's design an experiment to test our CD player. Let's take another CD and put it into that same CD player and see if that CD plays properly. Okay, you do that, and it turns out that the sound from that second CD is fine. Your CD player is working fine. So that, by the way, is your null hypothesis proven. You've kind of disproved that the CD player is faulty. So that hypothesis is wrong. You need to go back and ask yourself, well, what else explained that observation that my music keeps on skipping? Well, the other possibility is that my CD has a scratch in it, okay? Or something's wrong with that CD. So how do we test that hypothesis? Well, we take that CD, we go to our friend's house, we put it in their CD player, and see if the CD works there or not. Now, we find then that the sound still is skipping, and that then tells us that, well, this is a piece of evidence in favor of this hypothesis. This hypothesis is probably a good one, and there's something wrong with the CD. Maybe it has a scratch on it, or like a little scuff or something. So the theory that we come out of this with is that the CD has a defect on it. There's something wrong with that CD. Now, again, this was a really dumb example because no one sits there and, when their CD skips says, I must come up with a hypothesis on this. But they are effectively doing that at the back of their minds. And that's kind of my point here, that scientific thinking is really natural and it is a really good approach to solving problems. So even if you don't see yourself as a scientist, you really should, because this is kind of a good way to kind of just approach life when it comes to problem solving. Okay. Now, I've mentioned the word hypothesis and theory quite a bit, and you've probably heard the term law when it comes to something that we get out of scientific experimentation. And there's a lot of confusion over these three terms and what they mean. The reason for this confusion, I think, is the word theory means something different in science compared to regular vernacular English. So when you're speaking ordinary English, as not a scientist, as a regular person, you can say, oh, I have a theory on that. Like, this is what I think is going on. This is my theory on what's happening here. To a scientist, that's not a theory, though. That's a hypothesis. You're making a hypothesis, an educated guess on what's going on. But remember, to a scientist, a hypothesis isn't enough. Okay? So what is a theory to a scientist, right? Why do we trust theories in science? A theory is a summary of your evidence that supports a hypothesis, something that essentially says this is a good way to understand how this particular phenomenon works. Okay, so you can basically explain your phenomenon using this theory, right? But it's an explanation. Now, the problem with explanations of things is that you actually can't prove things. It's just impossible from a philosophy of science standpoint to prove anything with a theory, all right? Because there's an infinite world of possibility. Like, you can prove things to a really high confidence, but there's no 100% probability. Let me give you an example so you can see what I mean by that. So let's say we examine the statement, all swans are white. Okay, now that is, for most people, a pretty good hypothesis. If you see any swan anywhere in the world, like on any pond in any country, it's probably going to have white feathers, right? Like, typically that is how you would approach swans. If you arrive at a lake you've never been to and you happen to see swans there, it's a good prediction that those swans will have white feathers. Okay, so that's an example of a theory. Now, the problem with that, though, is that you have not been to every lake in every country all over the world and seen every single swan. It could be that there is a flock of swans that evolved over in New Zealand, right? It's untouched with any other swan population in the rest of the world, and they just happen to gradually develop like black feathers. This is, by the way, this is not a theoretical exercise. When I'm saying theoretical in the regular English way here, but this is actually a true thing. There is a flock of swans in New Zealand that has black feathers. And this is an example of that paradigm shift I was talking about, where theories can change to follow new evidence that comes to light. Okay, so again, the theory isn't wrong. It just needs to be modified slightly. Instead of saying all swans have white feathers, you say all swans have white feathers except for that one flock in New Zealand. And that's still a good theory of explaining what you're going to find when it comes to swan feathers. Okay, so again, that's why you can't prove anything with a theory. So does that mean we can never be sure of anything in science? No, of course not. That's, like I said, that's a great explanation for how to approach life, how to approach problems, how to approach a phenomenon. We know, like, we are relatively confident of this being true, so we can proceed, with that knowledge. However, can you prove things in science? While you can't prove things in theories, it is possible to prove things using what's called a law. A law is a mathematical proof for something. And that's the great thing about math. You can prove things in math. So, to give you an example of a law, there's the law of gravitation, right? That is a mathematical equation where you show the relationship between two bodies with mass and how they are attracted to each other through gravity. So the gravitational force of attraction between them is their masses multiplied by each other divided by the distance between them squared. You can write that out as an equation. So, for example, you could write the force due to gravity, F, is equal to some constant g times mass 1, mass 2, over r squared. Okay, so this is Newton's law of gravitation. Okay, but again, that's not important. This is a physics thing. You don't really have to worry about that for this class. But what I really wanted to draw your attention to is this equal sign in that equation. Again, this is why math is useful. You can prove things are equal to each other using math, and this is the power of laws. You can prove this relationship mathematically. All right. Now, again, that describes the phenomenon in terms of mathematical variables, but it's not really an explanation of how or why this is going on, right? So it explains how gravity, the variables in gravity like mass and distance are involved with each other. It doesn't really explain how gravity is or why it is, or helps you understand what is gravity doing. And that's kind of the difference between theories and laws, their pros and cons, right? Theories are great at explaining what's going on. They're a great way of understanding a phenomenon in that sense, but you can't prove things in theories. In laws, you can prove things mathematically, but that's really all you can do. They don't necessarily explain stuff. Okay, so that's, it's not like one's better than the other. It's just that they are used for different purposes. Okay, now with that being said, that brings us to measurements. Because I mentioned that in order for science to happen, in order to go from your hypotheses to a theory or law, we need to experiment. We need to collect data about our phenomenon and then analyze it and explain it, right? Well, what is data, right? Data is information about the system we're studying. So this comes in multiple forms. You can have what's called qualitative data, which is descriptions of things. So for example, if you're a biologist studying swans around the world and you are looking at various swan populations and observing the color of their feathers, swans are white is an example of qualitative data. Okay? Quantitative data is what we call measurements. We're measuring numbers that help us quantify the phenomenon we're observing. Okay, so what do we mean by a measurement? How do we take measurements, and what are they? In order to take a measurement, you need some sort of device, right? There's some instrument that helps you, well, measure whatever you're measuring. So, for example, you could use a yardstick to measure distance, or a meter stick if we're going to get into metric units, which we will in this class. Or you could use a scale if you're trying to measure how heavy something is, a thermometer to measure temperature, and so on. Now, whenever you use a measuring device or an instrument, it's going to give you two pieces of information. One is the units that you're measuring in. Okay, so there's going to be some unit that kind of gives that that gives your measurement context. So, for example, if you're measuring a distance, you could be measuring it in things like inches or meters or whatever, yards, right? If you're measuring a mass, you're measuring it in pounds or kilograms. Or if you're taking temperature, it could be like degrees Fahrenheit, degrees Celsius, degrees Kelvin, things like that. Actually, degrees Kelvin is not a thing. Technically, it's just Kelvin. You don't use a degree symbol. I'm getting ahead of myself. We'll talk about that in a second. The other thing that's really important besides the unit is, of course, the number itself, right? The units are important because they put things in context. You need a number. That's the actual measurement. Okay, so basically, yeah, whenever you take a measurement, those are two things that your measurement has to include: some number, which is the literal measurement you're making from your device, but also a unit which gives it context. I think a lot of students tend to forget the latter of those two things. They tend to forget to include units. They'll just write down the number. The problem is the units are really important for making sense of those numbers, right? To give you a silly example, if you're following a recipe and it says, okay, now add 6 of sugar, that makes no sense, right? Do they mean 6 teaspoons, 6 tablespoons, 6 cups, 6 pounds? That's a really loose term, or a really nonsensical term, rather. We need a unit to know, well, 6 what of sugar? Okay, so when I want you guys to get into the habit of writing out your units with along with a number when you make a measurement. Okay, so if you're measuring a particular length, don't say, oh yeah, that's 35. It's 35 meters or 35 centimeters or whatever you're measuring. Okay, so that brings us to the units themselves. I mentioned earlier that you can measure things in what we call metric units, or you could use things that are called English units or US customary units. Uh, Basically, metric units, even though you didn't grow up with them, you've probably grown up with US customary units or English units. The metric system is really useful when it comes to doing science. Okay, there's a derivative unit called the System International. So metric and System International aren't technically the same thing, but they're very similar. We'll see in a second. But basically, the key takeaways from the metric system is that the scaling up of units is centered on decimals. Basically, if you want to scale up something, it's in multiples of 10. For example, there are 1,000 meters in 1 kilometer. Okay, 1,000 is just 10 times 10 times 10. Okay, so that's kind of what I mean by scaling up a factor of 10. And that is way easier to convert than if I asked you, well, how many yards are in a mile? I don't know the answer off the top of my head, and I'd wager a few of you probably don't know either. And also the nice thing is that the scaling up is always some multiple of 10. So it's a little bit easier to remember. Whereas I think with English units, you run into that problem of the scaling up not being linear. So for example, there are 12 inches in a foot, but there are 3 feet in a yard, not 12 feet in a yard. You see? And likewise, there are not 3 yards in a mile. It's some number that's a lot higher than that. Whereas there are 10 centimeters in a meter, there are 10 meters in a decimeter, and so on. Okay, there's 10 decimeters in a 100 decimeters in a kilometer. But again, 10 times 10. So my point here is that it's a little bit easier to figure out how to scale things up, and I'm going to show you how to do that using the prefixes. I don't know if you noticed that those words, centimeter, decimeter, kilometer, all of them have meter at the end of it. It's just that prefix that tells you how much you're scaling by. So we'll get into that in a little bit. Okay. The other nice thing about the metric system is that it's very widespread. It's kind of weird. The only countries that don't use the metric system, at least in some capacity, are pretty much just the United States, Liberia, and Myanmar. So it's kind of weird to not see the metric system being used as really widely here. So that being said, even Americans who are scientists will use it in science because it makes taking measurements in science so much easier. All right, so what are these metric units, right? What are metric and what are system international units? So for the metric system and the SI units, we measure lengths using meters. Okay, we measure volume using either liters or cubic meters. We measure mass in grams or kilograms. We measure time in seconds, and we measure temperature in degrees Celsius or Kelvin. Now, just a quick note here before you start panicking, like thinking like, oh, these things are similar, but I've got to memorize both of these. To be honest with you, you're probably most going to use just the metric system. Physicists tend to use SI units more. Chemists tend to use metric units more. So don't panic. We're mostly going to do things on the scale of the metric system. The SI units are very similar. For example, a kilogram is just 1,000 grams, right? They're related to each other. But typically, you'll find that in chemistry, we weigh things in the scale of grams more often. Okay, now one exception to this is the Kelvin. When we get to gas laws, which involves a lot of physical chemistry, and remember, physical chemistry is derived from physics, you'll see that a lot of the laws that we study in gases, in gas laws, it involves temperature on the Kelvin scale. We actually have to use Kelvin for those laws to kind of make sense. I'm getting ahead of myself. When we get to that chapter on gases, you'll understand a lot more why we use Kelvin. So we're going to see how Kelvin work now in this chapter and in the next chapter as well. But you'll understand why we use Kelvin in much later on in the semester. Okay, so let's look at the actual units we're using and how we scale them up or down and so on. So when we measure things, really the three most common things you're going to measure when it comes to metric units, at least like new ones that you haven't seen before, involve measurements of length, of volume, and of mass. Okay, so we're going to examine those units in general, and we're going to then also see how to scale them using prefixes. I alluded to this earlier. But the nice thing you're going to see here is that these prefixes can be used across multiple types of measurements. So for example, the prefix milli means 1,000th of something. So a milligram is 1,000th of a gram, or a milliliter is 1,000th of a liter. Okay. But the nice thing is we can use that prefix for either of those. So let's talk about each of those quantities in general first. So length is a measurement along one dimension. All right. So I think most of you probably have a concept of what it means to measure the length of something. Now, in English units or in U.S. customary units, you use inches and feet and yards and all that fun stuff to measure distance. In the metric system, we measure using meters instead of feet or yards. So to put things in context for you, a meter is about a yard in length. It's actually 1.09 yards. And you don't have to memorize that equality there. You don't have to memorize that 1 meter is 1.09 yards. But I'm just putting that to give you kind of a visual, like a mental image of what a meter is. Okay, so if you take about one big step, or about a yard, that's the equivalent of close to a meter. Okay, now again, we can scale this up or down. So you'll find that we often make measurements, at least in our everyday lab usage, in centimeters. That's just a very convenient, smaller unit to measure with. Okay, so the word centi means hundred, so 1 meter is 100 centimeters. So if you want to put centimeters in context, if you're trying to visualize what is a centimeter, 1 inch is 2.54 centimeters. So if you have a ruler that has inches and centimeters on it, you'll notice that the 1 inch marking is about here on your centimeter scale. So we'll put past 2.5. While length is a measurement in one dimension, volume is a measurement in 3 dimensions. So how much space something takes up. All right, now we measure volume in when it comes to the metric system. We measure in things like liters, and we can scale that down into milliliters or scale it up accordingly. But I would say liters and milliliters are probably the most common volume measurements you're going to make when it comes to chemistry. All right, so we represent liters there with a capital L. If you want to put that in context for those of you, like since most of you have probably grown up with English units, a liter is about the size of a quart, roughly. Okay, so it's 1.06 quarts. Again, you don't have to memorize that, but just so that you can kind of visualize what a liter is. When you do this, our first lab, which involves conversion factors and problem solving, I think you guys actually do try this out. You're going to try and take a quart of water in a measuring cup and see how close that is to 946 milliliters, essentially. Okay. Again, you don't have to memorize that number, but just to put it in context, 1 liter is about 1 quart. Okay. Again, a liter is a large volume. We're going to often use smaller volumes and usually measure those in milliliters. Now, quick note here. You might hear a volume measured not in milliliters, but in cubic centimeters. So that's a centimeter cubed. Okay. So cubic centimeters. The thing with that, and this sometimes throws students for the loop because they're like, wait, what are cubic centimeters? That's just the SI version of writing down milliliters. A cubic centimeter and a milliliter are the same thing. 1 milliliter is equal or equivalent to 1 cubic centimeter. So if you ever see one written down and you're asked about the other, just realize they're the same thing. So if a question gives you a volume in milliliters, but you're supposed to find something that involves cubic centimeters, just realize you can still use that volume in milliliters. All right. Mass is a quantity that describes how, well, not quite how heavy it is, but really how much matter is contained in a particular object. It's a way to quantify how much matter something has. All right, so to tell you what I mean by this, like I was going to say how heavy something is. If we're going to get into the physics of it, that's kind of an oversimplification. What I mean by this is that mass and weight are not technically the same thing to a physicist. So, for example, if you weigh yourself on Earth and you weigh yourself on the moon, you would be lighter on the moon because the moon has less gravity than the Earth, right? So your weight would be lower, but your mass would be the same on both. Okay. That being said, when we weigh things, we usually use mass. So even though we often say, "Oh, I'm weighing this," what you're really doing is you're massing it. You're measuring the mass of the thing. So even though you probably measure mass in things like pounds and ounces, in metric, we use grams and kilograms. All right. So again, to put that in context, 1 kilogram is about 2.2 pounds. Okay. So that's the kilogram and grams. Those are the units we use. All right. And 1 kilogram is 1,000 grams. Again, I'll explain what these prefixes mean and how to memorize them in a little bit. Okay. Some other units that you're going to come across with the metric system, we've got temperature. Again, most of you probably use Fahrenheit a lot. So you probably say, oh, water freezes at 32 degrees Fahrenheit, and boils at 212 degrees Fahrenheit. Well, in the metric system, we use degrees Celsius. And the nice thing about degrees Celsius is it's determined using water. So water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So again, very, convenient scale there when you're looking at water, right? And since water is very useful for doing a lot of science and studying a lot of science, and a lot of the solutions we make use water as a solvent, using the Celsius scale is kind of useful when you're a scientist. Okay, the Kelvin scale is the Celsius scale shifted over. So to understand the Kelvin scale, I've got to first talk about absolute zero. The temperature negative 273 degrees Celsius is the absolute coolest you can possibly get. It is impossible to be any colder than that temperature because at negative 273 degrees Celsius, even atoms stop vibrating. There's no more potential energy for you to extract to make your material colder. Okay, so that's why we call that temperature of negative 273 degrees Celsius, that is known as absolute zero. Okay, so what is the Kelvin scale? Well, the Kelvin scale just takes that and sets absolute zero at 0 Kelvin. Okay, and then you just scale upwards from there. So there are no negative temperatures on the Kelvin scale. 0 Kelvin is the coldest you can get, and everything else from there is warmer. Okay, so if you want to convert between Celsius and Kelvin, all you have to do is add 273. Okay, so for example, if the temperature here is 25 degrees Celsius, basically that's 298 Kelvin. Okay, all right, don't stress too much about Kelvin right now. We'll get into more detail on that in the next chapter. All right, time I think is pretty straightforward. We use the same in all kinds of measurement systems. So we measure time in seconds. Of course, you can also treat that as any other metric unit, and you can scale that up or down using prefixes. So for example, a millisecond is 1,000th of a second. Right? A nanosecond is 1,000,000,000th of a second. Again, I'll explain what those prefixes mean in a second. Okay, moving on. So let's get to those prefixes I talked about. Basically, and this is one of those advantages of the metric system, we can scale up our units, and it makes sometimes it just makes sense to scale up or down our units depending on what we want to measure, right? So for example, if I was measuring the length of my desk, I would probably use meters to do that, right? Meters or centimeters or whatever. But if I wanted to measure the distance from here to Albany, I wouldn't want to use meters. That'd just be really inconvenient, right? I'd want to scale up and measure in kilometers, right? So how to scale up is kind of important. I mentioned this is one of the downsides to English units, right? Where you have to memorize how many feet there are in a yard and how many yards there are in a mile. And those numbers are not the same number. In the metric system, we can figure out what we're scaling up and down by looking at the prefixes on the words for the units. So for example, if we have a kilogram, the prefix kilo means 1,000. So we know that 1 kilogram is 1,000 grams, right? So we look at that kilo there, okay, and we know that that references 1,000. Okay, so 1 kilogram is 1,000 grams. That's all that means. So this does mean that even though I don't tell you you don't need to memorize any of the conversions between English units and metric units, because, well, like I said, English units are pretty much useless in this class. We're only going to use metric. You do need to memorize the prefixes we're going to use for the metric system. So your metric units will always start off with some sort of base unit, right? So we have meters to measure length. We have liters for volume. We have grams for mass. Okay? How we scale up or down is determined by the prefix we use in front of those words. And again, you can use the same prefix for all metric units. Okay, so let's start off by scaling up. I think that's a little bit easier. So basically, when you scale up, I think the simplest units we're going to use, the simplest prefixes, are where we scale up by 1,000 or 1,000,000 or 1,000,000,000. Okay, now this might be easier for you guys to remember because you probably come across these prefixes all the time when dealing with computer storage. So with 1,000, we use the prefix kilo. Okay, so kilo is represented with a lowercase k, and it references 1,000 of whatever it is. So a kilometer is 1,000 meters. So the symbol for a meter is a lowercase m. So if we wanted to show a kilometer, we'd write lowercase k and lowercase m. Okay? Now, let's say we scale up from there. What is a million of something? What's the prefix meaning a million? The prefix for a million is mega. Okay? And it's represented with a capital M. Okay? And you've probably heard this from computer storage, right? You've got a kilobyte, then megabyte, and then I guess you can probably guess what is a billion. It's going to be giga, right? Like a gigabyte. So let's scale down now. So if that's scaling up, kilo and mega and giga, how do we scale downwards to smaller things? Well, milli is a millionth of something. Okay, or sorry, I take that back. Is a thousandth of something. I know that's kind of confusing because you think of the word million, but milli is a thousandth in Greek. So while a kilo is 1,000 of something, milli is 1,000th of something. There's 1,000 millimeters in 1 meter. There's 1,000 milliliters in 1 liter. There's 1,000 milligrams in 1 gram. Now, while capital M represents mega, or a million, lowercase m represents milli, or 1,000th of something. Micro is a millionth of something. Okay? Now, we've run out of letters to represent m. We've got capital M for mega, we've got lowercase m for milli. And since micro is also an M word, at this point we're using the lowercase Greek letter mu. So if for those of you trying to write that out by hand and you want to say, okay, how do I write mu? Basically, you would write that out by hand like this. It's kind of like a backwards U with a little stick on the left-hand side. Okay? So I kind of made the second half of it a little bit long. So, but yeah, basically it's something along those lines. Okay. If you want to get even smaller than that, a billionth of something is nano, represented with lowercase n. Okay, and again, that's how you would scale downward. So just like this is 1,000, million, and giga is a billion. I've got that in the next slide. With milli, micro, nano, you've got 1,000th, a millionth, and a billionth. Okay. Now, in terms of in between your base unit and milli, we have some breakdown here where it's a little bit more convenient to have something in between 0 and 1,000th. So a tenth of something is deci, represented with a lowercase d. So a decimeter is a tenth of a meter. And then we have centi, represented with lowercase c. So that's a hundredth of something. Okay. So yeah. So again, depending on the scale we're going with, having these prefixes is kind of important. I think I used the example of measuring my desk in meters. I'd probably use decimeters maybe as well. But if I wanted to measure the distance between here and Albany, I'd use a kilometer, right? Well, the same thing goes for when you're scaling down to smaller and smaller things, right? So if I want to measure, let's say, the width of a hair, now I'd use micrometers to measure something that fine. When we get down to nanometers, now we're talking about the size of atoms. Okay, when we get down to that scale. So again, like the scale we're using, being able to scale up or down is just convenient for us. Okay. So again, here's a table. Feel free to pause at this table at some point, or just have this out when you're trying to do your homework. Eventually, you're going to get better at memorizing these. Like I said, with some things, like especially with the larger ones, just seeing them in regular everyday words helps. Like with computer storage, like kilobyte, megabyte, gigabyte, terabyte. That's where those words are probably kind of familiar to you. With the smaller ones, those are probably a little less common, so you do kind of have to memorize them. I will say that this table does go beyond what you need to know. To be honest with you, you're probably not going to get anything beyond mega or giga. You're definitely not going to be asked about tera as a prefix. Likewise, you're not going to go beyond nano, so don't worry about pico or femto as prefixes. You're really not going to get asked about those. I just included this table because I thought it was kind of neat, and just in case any of you were curious. Okay, so yeah, so the thing though is you do have to memorize those prefixes, and it just comes with practice. I didn't grow up in the U.S. I grew up with a metric system, so it's probably easy for me to say that just because I grew up with it. But like I said, even I had to learn it as a kid, and I think what really helped me was remembering those thousand increments when I was learning it. So at least even if it's a little bit harder to remember centi and deci, though to be honest with you, I guess I remembered centi as just from using it kind of like how you use inches. I measured things in centimeters. It is easier sometimes to remember just those thousand um, denominations. So kilo, mega, and giga is thousand, million, and billion. Milli, micro, and nano is a thousandth, millionth, and billionth, respectively. Okay. If you do want to memorize all of these, there are memory devices out there that can help you with that. I remember back when I used to teach high school, a lot of my students who came into class would tell me that they had used a memory device along the lines of King Henry died while drinking chocolate milk or something like that. I don't know what the exact acronym is, but you may be familiar with something like that from high school yourselves. For those of you who didn't hear that before, just Google it. I'm sure there are other memory devices out there that are kind of useful. But my point here is that you do want to memorize these units and get comfortable with those abbreviations for them, those symbols for them. Okay, so when we change our units, we often do that out of convenience, right? As I mentioned, I don't want to measure the distance from here to Albany in meters. I'd probably want to scale up to kilometers. However, sometimes you can't always do that. You sometimes need to compare numbers in the same units, but this results in some numbers being really weird. Okay? Chemistry or science in general, but like really with chemistry, where you're dealing with really tiny, tiny things, you can get some really ridiculous numbers, either really, really big numbers or really, really small numbers. Okay. And writing these out can be kind of a nightmare if we had to write them out as regular numbers. Okay. Because we'd have to deal with a lot of zeros. And that's really quite a pain. I'll show you on the next slide of an example of why this is a big deal. So to make things easier for us, we use what's called scientific notation. Scientific notation is a standard way of writing out numbers so that they fit really neatly and concisely. They're in a very short form and a very easy way to understand kind of what scale we're dealing with. So they're always in this format where you have some number, some coefficient, multiplied by 10 raised to a particular power. Okay? So what are these powers? These are multiples that you're moving your decimal place by. I'll show you some examples in a second. Okay, so let's take a really silly example, the number 703. Now, the number 703 is easy enough to write out. If we were to write it out in scientific notation, we would write it out as 7.03 times 10 to the power of 2, right? So this number is originally 703, okay? But if we were to write it out in scientific notation, this is how we would write that out. Now, just a little terminology here. What are these different terms? What are the different parts of this number? We have what's called a coefficient. That's the 7.03 at the start of the number. We have the exponential term, which is times 10 to the power of 2. And then the exponent itself is that number that the 10 is raised to. Okay? And that's going to be very important. The exponent is very important to us for telling us the scale on which we're dealing. All right? This coefficient is always a number between 1 and 10. Okay? So that decimal always has only one number, one digit before it. Okay. The exponent tells us how many places over we move that decimal point. Okay, so 10 to the power of the 2 is the same thing as 100. We would take 7.03 and multiply it by 100 to get us the original number, 703. But perhaps it might be easier to think of it as that 2 is telling us that we need to move that decimal point 2 places over to the right. Okay? Now, that of course is a positive exponent of 2. If we had a negative number for that exponent over there, we would move that decimal point to the left because that negative exponent tells us that the original number is really small. It's a number smaller than 1. It's 0 point something. Whereas a positive exponent like 2 tells us that the number is greater than 1. In this case, 703. And that scale, the size of that exponent, tells you just how big a number are we dealing with. Like, what kind of scale is it? So why is this important for science, especially for chemistry? Again, we're dealing with some sort of ridiculous numbers when it comes to chemistry because we deal with really, really tiny things. So here we have a cup of water, a glass of water, and it's got really, really tiny water molecules in it. Well, that simple glass of water has a lot of those really, really tiny molecules in it. This many, in fact. And I don't want to say it out because I would have to say a lot of zeros if I was writing that number out. Okay? And of course, you can see how much space this number takes up. Right? That's a really long number. And it's kind of a pain to write out. And really kind of hard to write out accurately. What if I miss a zero or accidentally add an extra zero? But instead, I could write that out as 7.91 times 10 to the power of 24. That's a lot, takes up a lot less space, and it's a lot easier to say. All you have to realize is that there's this sort of decimal point that's not shown at the end of the number, because it's a whole number. If I move that 24 spaces to the left, I would move that decimal point here between the 7 and the 9, and so there's my coefficient that's between 1 and 10. And of course, I show that I've moved the decimal point there 24 spaces by using an exponent of 24. Likewise, each molecule itself is really, really tiny and therefore very, very light and weighs only this much in grams. And so this is a really tiny number. So I know that my exponent is going to be a negative number there. So it's 2.99 times 10 to the 23. And that's because I would have to move that decimal point 23 spaces to the right here to get that coefficient of 2.99. Okay, so again, remember, you want your coefficient, that number at the front of your scientific notation, to be a number that is greater than 1 but less than 10. Okay, so let's practice this. Let's take a second and try this out. Okay, so basically, when you have a number and you're trying to write in scientific notation, figure out first where is the decimal point in the number. If it's a whole number, there is no decimal point, so you have to understand that it's there, it's just kind of imaginarily written to the right of the number. Okay? You now want to move your decimal point so that your coefficient is a number between 1 and 10. So you've got to ask yourself, how many spaces am I moving my decimal point? And that number of spaces winds up being your exponent. Now, of course, if you have a really small number that you're starting off with, 0 point something, you need to move that decimal point to the right to get a number between 1 and 10. So your exponent then is going to be a negative number. Likewise, for a large number, you're going to move that decimal point to the, basically, you're going to move that decimal point to the left to make your number smaller. And you're going to write those number of spaces as a positive exponent. So let's try a couple of practice problems here so we can see how that works. Okay, so let's try. I'll go through the first couple with you, and then I'm just going to skip on ahead. The PowerPoint here will have these answers, but feel free to pause this video to give yourself more time to try these, or to just skip on ahead. Okay. So let's start off with that first one, 12,500. Okay, so when I look at that number, I see that I've got a decimal point that's not shown here. This is a whole number, so I know there's an imaginary decimal point at the end of the number here. Now, where do I want my coefficient? Well, I want a number that's greater than 1 and less than 10. So where would I put a decimal point in this number so that I have a number that's greater than 1 and less than 10? Well, probably between that 1 and that 2, right? Because that would give me a coefficient of 1.25, right? But how many places do I need to move that decimal point over to wind it up there over between the 1 and the 2? That's 1, 2, 3, 4 decimal places to the left. So my exponent winds up being 4, and I would write this out as 1.25 times 10 to the power of 4. Okay. Now, where did those zeros disappear to? Well, remember, those zeros are kind of just placeholders holding that decimal point, that imaginary decimal point in place. Those zeros aren't actually important. We say that they are insignificant. I'll explain exactly what that means in a little bit. Okay, let's try another example with a small number. So notice that we have a very small number, a number that's less than 1. So we're going to move this decimal point over to the right to get our coefficient. So where would we move that decimal point to have a coefficient that's greater than 1 but less than 10? Well, if I move that decimal point between the 2 and the 0, I get a number of 2.02, right? And that's a number that's greater than 1 and less than 10, right? It's 2.02. So how many places do I move that decimal point over to get to over here, to get 2.02? I've got to move it 2 places to the right. So my exponential term will have an exponent of -2 because I moved it 2 places to the right. So my coefficient is 2.02. It's my number between 1 and 10. And my exponential term is times 10 to the power of -2. Okay. So again, notice that that those leading zeros kind of disappear. Again, they're just kind of placeholders that keep the decimal point over there. Okay, but when you move the decimal point over, they kind of disappear because, well, they don't need to be held anymore. It's kind of silly to say it's 002 when you can just say, well, it's 2. Okay, so I'll let you try these other 2 examples by yourself. I'm just going to skip through the answers, but feel free to pause this video if you want to take more time to try it out yourselves, okay? So I'm going to go ahead and skim through these. All right. Now, let's say we want to go backwards. We are given a number in scientific notation, but we want to write this out in standard form. Okay, where do we move how do we write out our number? Well, we go backwards, right? We're still moving our decimal point, but now we're going to move it into the opposite direction than we would to write the number in scientific notation. Okay, so if you have a positive exponent in your number in scientific notation, you need to move your decimal point that many spaces to the right. Okay, and if you have a negative exponent, you move it that many spaces to the left. Okay, if you ever get mixed up, by the way, and I don't blame you, I did when I was a student, the easiest way to remember is that a positive exponent means that your answer should be a big number. Okay, so when you're done moving your decimal point to the right, that's how you can confirm that you did it correctly. You get a big answer. Likewise, with a negative exponent, that tells you that the original number was a really small number. So you know your number is going to be 0 point something. Okay, now what happens when you get to the end of a number, but you still have to move it more spaces? This is where those placeholder zeros come in. You start inserting zeros to help push your decimal point where it needs to be. Okay, so let's try an example here. So here we have a number 6.442 times 10 to the power of 5, and that is a number in scientific notation, right? It's got our exponential term over here times 10 to the power of 5. So that exponent of 5 tells us that we need to move this decimal point 5 spaces over. Now I'm going to move it over to the right because I know that that positive number 5 tells me my answer is going to be a pretty big number. Okay, so let's move it 5 spaces to the right. So if we move it 1 space over, it comes over to 4 point. So we move from there to there, that's 1 place. That from there to there, that's 2 places. And then from there to there, that's 3 places. But we need to move it 5 places, so we need to go 2 more, right? So that might be a little harder to see. Let's try drawing it like this. Let's draw the number out. So we have 6.442, right? We've moved this 1 space, 2 spaces, 3 spaces. We want to move it 4 spaces and 5 spaces. So to make this number work, we have to have that decimal point wind up over here at the end, we need to push it there by inserting zeros. Okay? So our number is actually going to be 644,200. Okay? All right. Let's try another one that's similar. So here we have 5.583 times 10 to the power of -2. Okay, so again, that negative exponent there tells us that we're going to move this 2 spaces to the left. Right, so we have 5.583, and we're going to move this 1 space, 2 spaces to the left. Now, again, we need to put a placeholder 0 here to keep that decimal point over there. So we're going to put a 0 over there. So our answer is going to be 0.05583, or more commonly written, when you have a decimal point at the start of a number, you usually write it as 0 point something. So even though you might, just verbally say 0.05583, oftentimes it's usually considered, just more complete to write out that 0 before the decimal point as well. Okay. So again, be sure to practice this to get the hang of it. But the more you practice it, the more sort of second nature it's going to be. For this class, you need to be comfortable reading an answer in scientific notation or regular standard form. When you do any calculations, because our quizzes and exams are multiple choice, you have to be ready to see the right answer as one or the other. Because sometimes your calculator will give you the answer in standard form, but the answers on your multiple choice are all in scientific notation. Or vice versa. Sometimes your calculator will give you an answer in scientific notation, but all your answer choices are in standard form. So you need to be ready to convert one to the other, or at least recognize one versus the other. Now, quick note here about using a calculator for this. Depending on the calculator you have, there might be different ways to write a number in scientific notation. Okay, so you might be tempted to type out the whole number in scientific notation using a multiplication sign. So for example, if you had the number 5.583 times 10 to the power of -2, you would write that out as, basically you would try typing that out as 5.583 multiplication sign 10, so 1, 0, exponent or caret, negative, and then 2. That's a lot of keystrokes. And also the problem with that is that your calculator sees that as 3 separate numbers. It doesn't realize that's one number in scientific notation. Okay, so what I recommend is to look for your calculator's exponential key, or sometimes listed as the EE button. Okay, different calculators have this in different places. If you aren't sure where yours is, just come talk to me during office hours. I've seen like a billion calculators. Just maybe take a picture of your calculator and email me what it looks like, and I can show you where it is on there. And we can get through that. It's pretty straightforward. But basically, the way they all work is when you press that button, it will substitute out the times 10 to the power of part of your number in scientific notation. Depending on your type of calculator, it'll either write that out or it might swap it out for a capital letter E. All right, so that would be, if you see your calculator saying 5.583E negative 2, just realize that it's just saying the same thing in scientific notation, where the E means times 10 to the power of. Okay? So this is another way it's shown displayed on your calculator. So be wary of that with the type of calculator you have. For example, it's sometimes hard to see that E if you're not looking out for it. So that can really change your answer significantly, because your, so for example, if you only saw those first few digits and you just saw that you wrote down your answer as 5.58, for example, and you just rounded it off there, 5.58 is really different from 5.58 times 10 to the power of negative 2, because that's 0.058. Okay, so watch out for that. When you'll start getting in the habit of looking towards the right of your numbers in your calculator to see, keep an eye out for that exponential term. Okay. Okay, so that brings us then to the term I mentioned earlier about significant figures. Why are numbers significant or not, or insignificant? And why is that important? Why do we care if numbers are significant, or how we determine those significant figures? Let me give you an example to show why this is something we care about. Okay, so imagine that you went to a museum and you saw a fossil, and you asked the curator, how old is that fossil? How old is that dinosaur that I see in front of me? Now, if the curator said something like, this dinosaur is 65 million years, 3 months, and 8 days old, well, my first thought would be, that's oddly specific, right? Well, how can you be so sure that it's exactly that, right? That's really accurate for something that's really old, and you can't be sure of that, right? Well, the curator in this case says, well, when I showed up here on my first day of work, I was told it was 65 million years old, and I've been here for 3 months and 8 days. Now, does everyone see the problem with that logic? The problem, if you haven't figured it out yet, is that the curator here took a really fuzzy, imprecise number, 65 million, right? When you say that fossil is 65 million years old, you mean it's about 65 million years old. And they took a very precise number, 3 months and 8 days, something they could measure in their own lifetime because they were there. And they tried to smush those two numbers together. And the problem is you can't take two numbers with two different precisions and treat them equally, all right? That's why significant figures are important. They help us understand how do we treat the different precisions of numbers. And so when we do calculations, what digits can we trust? How should we write out the answer that our calculator spits out? Okay, so let's first understand what these significant figures are. Okay, or how do we determine them? So to understand that, I first have to tell you there are two types of numbers out there. Okay, we have what are called exact numbers or counted numbers, and then we have measurements, okay, which we've been kind of going on for quite a bit. So as you can probably guess, we're going to talk a fair amount about measurements. Counted numbers, as the name suggests, are called that because you can get them by counting. They're also sometimes called defined numbers, but the key thing is that these numbers are treated as exact. That means they have an infinite amount of precision. We can write down an infinite number of significant figures, or treat them as having an infinite amount of significant figures. The reason for this is that, again, because you're counting something, you are infinitely sure of that number. So for example, if I say there are 4 chairs in my living room, it's exactly 4. That's the number I count. So I could write that down as 4.00000000 ad infinitum, and that's still true. Okay, and it's kind of understood that I mean that when I say there are 4 chairs. Okay. Likewise, any numbers that are defined, if you have a relationship that's defined between two quantities, Okay, and that's just a standard definition. Again, you can treat that as having an infinite amount of precision. So if you say 1 kilogram is 1,000 grams, that's the same thing as saying 1 kilogram is 1,000.0000000 grams, so on. Okay. Likewise, 1 minute is 60 seconds. That's the same thing as saying 1 minute is 60.0000, and so on, seconds. Now, when it comes to measurements, though, we don't have that kind of certainty. The reason for this is that the instruments we use, the devices we use to measure our numbers, are not perfect. They're just limited in their precision. They can't have an infinite amount of precision, right? That's just the way reality works. So you are limited by the precision of the instrument you're using. Your measurement's only going to be as precise as the maximum precision on that instrument. Let me give you an example here. Okay, with a ruler or scale, so measuring like a ruler here, we have the number of divisions on our ruler that define how precise it is. So for example, I know these two rulers look the same, but this one on top is as it appears, right? So if you look at each of the markings on this ruler on top here, each of those divisions is for 0.1 centimeters. So each of these big divisions is a centimeter, so 1, 2, 3 centimeters. And here we have 10 smaller divisions. So each of them is 0.1 centimeters, right? So that's 1 centimeter, that's 1.1, 1.2, 1.3, etc. Okay? If we were to measure this nail using this ruler on top over here, we see that it's somewhere in between 2.8 and 2.9, right? So here's the marking for 2.8, here's the marking for 2.9. It's somewhere in between there. So we're a little bit uncertain of what that measurement exactly is, what that last decimal place is. Depending on how you look at it, you might write it down as being 2.8, you might write it down as being 2.9. If you're really not confident, if you really think it's really in between both of these, you could write down 2.95, but that 5 is really uncertain. You can't really be, 2.85, my bad. That 2.85 is really uncertain, right? That 5, you're totally guessing on that 5, right? Well, let's look at the ruler below it. Now, this is the same nail, all right? But this ruler we're going to use for the second measurement over here has even smaller markings between the 0.1 centimeter markings. So in other words, it goes to 2 decimal places. It goes to the nearest 0.01 centimeter. So I know that my nail is somewhere between 2.8 and 2.9 centimeters. If I zoom in, I can see on this ruler that it goes to exactly 2.85 centimeters. Okay? That's a more precise measurement because that second ruler is more precise, even though it's the same nail. It's not like the nail changed in length. It's the ruler that we used that changed the measurement. Okay, so that's something you've got to be aware of. When you see a measurement written down, okay, so something that is not an exact number, if you see a number in a problem, that measurement has to be treated to the right, you have to gauge that precision that measurement's written down with when you do calculations with that number. Okay, so we use significant figures as a way to sort of gauge that precision. So to use the example here with our two measurements of our nail, here we have 2 significant figures. So let's say I said that this nail was 2.8 centimeters using this scale. The 2 and the 8 are significant, so those are 2 significant figures. If I look at this measurement, 2.85, the 2, the 8, and the 5 are all significant digits, and so that's 3 significant figures. Okay? So this is a more precise measurement because it's got more significant figures. So when I see these numbers written out, I need to make a note of how many significant figures there are because that's going to be important when I try to do my calculations. Okay, so how do we look at a number and determine its number of significant figures, right? How did I figure it out for the previous slide? How did I determine the number of significant figures for those two measurements? In the previous slide, that was relatively straightforward. Those non-zero digits, the 2 and the 8 and the 5, they're all significant because they are non-zero numbers and they were written down for a reason. Okay? So I think things get a little bit more complicated when we have zeros in our number, because we've got to figure out, while all non-zero numbers are significant, zeros may or may not be significant depending on where they are in the number. So let's look at three scenarios here. We have what are called leading zeros, which are to the left of the number. Okay, so if your number starts with zeros, however many zeros there are on the left of the number, no matter where there's a decimal point in those, all the zeros on the left of a number are never significant. If you have any captive zeros, so those are zeros that are in between non-zero digits, those will always be significant because they're trapped within non-zero digits, which are always significant. They too are significant because they have to be in order for those digits on either side of them to also count. Trailing zeros are the trickiest ones. So trailing zeros are zeros that are to the right of the number. Okay? That depends. Trailing zeros may or may not be significant. They're significant if there's a decimal point anywhere in the number, because then those trailing zeros were written down for a reason, and that means that they are significant. If there's no decimal point in the number, then those trailing zeros are just there as placeholders, and therefore they are not significant. Let me give you a few examples so you can see what I'm talking about. So let's go back to the example of our fossil, and we have the number 65 million. So that's 65 followed by 6 zeros. Now, how many of these digits are actually significant? So I know my 6 and my 5 are significant, but what about these zeros to the right of the number, to the right of those non-zero digits? Well, remember, these are trailing zeros if they come to the end, right? So you have, captive zeros in the middle, in between non-zero digits. You have leading zeros on the left, and you have trailing zeros on the right. Okay, so these trailing zeros may or may not be significant, right? So just a reminder here. So leading zeros are never significant. Captive zeros are maybe significant, or sorry, captive zeros are always significant. And trailing zeros may be significant. Okay, so these trailing zeros here may or may not be significant. How do we know? Is there a decimal point? That's the question you should ask yourself. Is there a decimal point written in this number? In this case, there's no decimal point. So that means that those trailing zeros are not significant. And that's why it's only the 6 and 5 that are significant, and that's why this number has only 2 significant figures. Okay? Now, let's look at this number over here, 5,000.0. So again, our 5 is going to be significant as a non-zero number. Look at the zeros over here. They're to the right of the number. They're trailing zeros, so they may or may not be significant. Does this number have a decimal point? Yes, it does. That decimal point over there tells us that all of these trailing zeros have to count. Okay? So that means that not only is that 5 significant, but so is this 0, this 0, this 0, and this 0. So that's 1, 2, 3, 4, 5 significant figures. Okay? Now, let's look at this number over here. Here we have a 5. We know that's going to be significant. And we have all of these zeros here written to the left of it. So remember, these are what we call leading zeros, and leading zeros are never significant. So the only significant figure is that 5. Okay, so that's why there's only one significant figure. And then the last example here is 0.000050. Now this is an interesting case, because here we have that 5. We know that's definitely going to be significant. But now here we have two examples of zeros. We have leading zeros to the left, and we have a single trailing zero to the right. Remember, leading zeros are never significant. Trailing zeros might be significant, but we've got to ask ourselves, is there a decimal point in the number? And yes, there is a decimal point over here. So that trailing zero is going to count. And that's why there's two significant figures in this number. Okay? The question of if there is a decimal point or not only applies to trailing zeros. It only affects whether or not trailing zeros are significant. For leading zeros, it doesn't matter whether or not there's a decimal point, because with leading zeros, there is going to be a decimal point, but it doesn't affect that. Okay, that probably sounded a little confusing. It takes a little bit of practice to get the hang of that. Okay, so it seems a little clunky at first, but the more practice you do with that, of recognizing the number of significant figures in a number, that will make that more second nature. And so I really recommend doing the conversion factors and problem solving lab worksheet, because the first part of that worksheet pretty much just gets you to practice this concept. Definitely also practice the homework, for the same reason. Now, what do we do with numbers when we realize, oh, we've got the wrong amount of precision here, and I've got to round off a number, I've got to cut off a number because it's written incorrectly? All right. So you're going to get to a point where you have to round off numbers. Now, again, I'm going to stress this. You'll see this in our second lab with density, when we start making some measurements to do density calculations. When you make a measurement, you need to write down whatever your measuring device gives you. That's all important information. It's when you do calculations that you've got to determine where you round off a number, or how far do you have to round off a number. But before we get to that, let's ask ourselves, how do we round a number? The way to approach this is that you look at where you're cutting off the number, and the next digit, in other words, the first digit that's going to be cut off, if that number is 5 or greater, if it's equal to or greater than 5, you're going to round up. Okay, so the last digit on the number that you keep increases by 1. Likewise, if that digit that gets cut off is less than 5, then you just cut off that part of the number. Okay, it just truncates the number. It rounds down, so to speak. Okay, so here are some examples so you can see what I'm talking about. So let's say our calculator gave us the number 8.4234, and we know that we've got to write that answer to 3 significant figures. So I know that my 8, my 4, and my 2 are significant, but I've got to cut off the number there. Okay, and so I've got to look at that 3 to determine whether or not I round up. Well, 3 is less than 5, so I just write 8.42, and I just stop there. Okay, let's try another example. Let's say we had 14.780. So again, if I want to write that to 3 significant figures, I have a 1, I have a 4, and I have a 7. Those 3 are significant. I've got to look at that 8 to determine whether or not I round this. Okay, well, 8 is greater than 5. And remember, if something is 5 or greater, we have to round up. So the 7 gets rounded up to an 8. Okay, so it becomes 14.8, and that's why we have to round that up accordingly. I pointed this out earlier when I talked about numbers in scientific notation, but basically we sometimes use zeros as placeholders, and you can see this here as well when we've got to cut off a large number, but it's still a large number, and cutting off a part of that number changes the number. Here's what I mean. For example, here we have 3,262, and we want to give that to 3 significant figures. So we want that 3 to count, the 2, and the 6, but that's all we can write down for digits of value. We've got to get rid of that 2. Okay, now first things first, that 2 is less than 5, so we don't round that 6 up. It just stays a 6. Do we just remove the 2? Do we write 326? The problem with that is that this is 3,262. And we have, if we wrote 326, that would be 326. So we have to put a placeholder 0 here to show that that 3 is still in the thousands place. Okay, so it's not so much that we're cutting off these numbers when we round off, it's more like we're swapping them out for zeros. But in the case of decimals, they kind of don't show up. So if you're having trouble visualizing this or understanding why that's the case, it might be easier to see this if we wrote this out in scientific notation. So if we took 3,262 and we took that imaginary decimal point, realize we move it 1, 2, 3 places to the left, so that would actually be 3.26 times 10 to the power of, oh sorry, I took that back, 3.262. Oops. So that's 3, oops, let's go back. There we go. So that's 3.262 times 10 to the power of 3, right? Because we moved that decimal point 3 places over to get back to the original number. Okay, so here's that number written with 4 significant figures, but again, if we want to write that to 3 significant figures, we would drop that 2. So now we have 3.26 times 10 to the power of 3. Well, again, if you want to write that out in standard form, you need to move that 3 places over. So that goes from over past the 2, past the 6, past one more spot, and that's where we've got to put that imaginary 0 in. Okay, and that's what makes the number 3,260 accordingly. Okay, and again, you can see this in more detail if we were trying to take those same numbers and write them to 2 significant figures. You can see here how that's 3.3 times 10 to the power of 3, and that's why we write that as 3,300. Okay, the 2 of course gets rounded up because the next digit dropped is a 6, which is 5 or greater. All right, again, this is one of those things that comes with practice, and I really recommend doing the homework and the conversion factors lab where you get to practice this some more. And again, if you get better at recognizing this, it makes your life a lot easier. Now, why are we doing this? Why are we looking at the number of significant figures and then determining whether or not we round stuff off? Because I just mentioned we don't do this for measurements, right? When you measure something, you shouldn't round off your measurement. You should write down whatever your ruler or scale or whatever instrument you're being given, you write down what that's telling you. Well, the reason for this is that if you're not making the measurement, if the measurements are given to you, you need to know what precision were those numbers written down by. And then when you do calculations with them, how do you treat those numbers together? This was the heart of the problem I had earlier with that fossil in the museum, where the curator was using a number with very low precision, with 2 significant figures, to a number with really high precision. Combining those 2 answers didn't make a sensical answer. The answer didn't make sense. So you have to look at the precision, the number of significant figures, or in some places decimal places, and determine what is my least precise measurement, and then give out your answer accordingly. So to do this, we need to look at 2 different scenarios when it comes to calculations. We have problems where we do multiplication and division, and we have problems where we do addition and subtraction. Okay, so when it comes to multiplication and division, we're going to look at significant figures. When it comes to addition and subtraction, we're going to look at decimal places. All right, so we'll look at both of these scenarios in 2 different cases. Okay, so like I said, with multiplication and division, you want to look at the number of significant figures for all of the numbers in your calculation. Whatever is the smallest number of significant figures, that's the precision you want to give your answer to. Okay, your answer is only as precise as your least precise measurement. Okay, so to use the example with the curator and the fossil, he should have just said that it's 65 million years old, because since that's not a very precise number, that's the only answer he can give with any confidence. Okay, to try and give a more precise answer would involve making stuff up. Okay, so let's see an example so you can see what I'm talking about. So here we have a calculation. We've got 0.1021 times 0.082103 times 273 divided by 1.1. So a whole bunch of multiplications and one division here. Now, you can plug this into your calculator easily enough, and your calculator will give you an answer of 2.080438. Okay, and that's great. Do you write down all those digits? And the answer is no, right? This is your calculator just doing what a calculator does, right? It's a computer. It just writes out all the numbers given to it. It doesn't do precision calculations for you. So this is where your job comes in. You've got to look at each of these numbers and ask yourself, what are the number of significant figures for each of these numbers? So 0.1021, how many significant figures does this number have? Well, the 1 significant, and obviously the 2 and the 1 at the end. Here we have a trapped 0 between them. Now remember, trapped zeros are always significant because they're between significant numbers, so they themselves have to also be significant. Does this leading 0 over here have to be significant? And the answer is no, it's not, right? Leading zeros are never significant. Even though there's a decimal point in this number, that doesn't matter. That leading 0 doesn't count. So that number has 4 significant figures. That 1, the 0, the 2, and the 1. Okay, so similarly, look at each of these numbers and ask yourself, what are their significant figures? So for this second one, we have 8, 2, 1, 0, and 3, because again, we have a trapped 0 here. And again, these leading zeros are not significant, so that's 1, 2, 3, 4, 5 significant figures. The next two numbers are going to be much easier, right? 2, 7, 3, that's 3 significant figures. And 1.1, that's 2 significant figures, right? The 1 and the other 1 are both significant. So let's look at these 4 numbers. Out of these 4 numbers, which of these is the least precise? This one here. This one only has 2 significant figures, which means our answer should also be given to only 2 significant figures. So we count the 2, we count this 0, and that's where we're going to cut off our number. Though we've got to look at that 8 and ask ourselves, do I round up or not? And since 8 is greater than 5, and you round up if you have 5 or greater, that 0 runs up to a 1, and my answer is going to be 2.1. So even though my calculator gave me this long decimal, I can't trust any of these numbers because this number is not precise. And that's why I can only trust an answer rounded off to 2.1. Any of those numbers afterwards are just kind of guesswork. Your calculator doesn't know that it's guesswork, but that's kind of what's happening. So you've got to look at that and determine that yourself. Okay, so that's with multiplication division, right? That's where we look at significant figures. Addition and subtraction is a lot easier. With addition and subtraction, we look at the number of decimal places. The same principle applies, though. We still want to write down our answer to the same precision as our least precise measurement, the one that has the least number of decimal places in this case. So let's try another example here. So here we have 171.5 plus 72.915 minus 8.23. And again, if you plug that into your calculator will spit out this number going to the maximum number of decimal places. But remember, you can't trust all of those. Okay, so to figure this out, let's look at the number of decimal places for each of our numbers in our calculation. Now, decimal places, as the name suggests, are the number after the decimal point, the number of digits after your decimal point. So 171.5 only has that 5 after the decimal point, so that is 1 decimal place. 72.915 has a 9, a 1, and a 5 after that decimal point, so that's 3 decimal places. And of course 8.23, that 2 and 3 are your 2 decimal places. So look at your 3 numbers. which one of these has the least precision? 1 decimal place. So your answer must also be given to 1 decimal place. So we're going to count that 1 that's after the decimal point, and we have to look at the 8 that follows it to determine whether or not we round up. Okay, so 8 is greater than 5, so that 1 is going to round up to a 2, and we write out the answer as 236.2. Okay, again, I have to stress this uses decimal places, not significant figures. So you have to watch out for the type of mathematical operator you're using. If you're using multiplications and divisions, you've got to count the number of significant figures for the entire numbers in your calculation. If you've got addition and subtractions, and you don't need both, you just need, like, either one will also use the same principle. So if you were adding 3 numbers together, you would still go off the number of decimal places. But yeah, you need decimal places to determine your precision. Okay, it's the number of places after your decimal point. Okay, so I mentioned that we are doing calculations where we're adding things together, we're multiplying, dividing. Why do we do this? Well, oftentimes we do a lot of our multiplication and division when we're trying to convert one quantity to another. Okay, so I'm going to get into conversion factors in a second, but to understand that, I first have to explain what are equalities. An equality shows the relationship between two quantities, between two things. And they're called equalities because there is an equal sign in that relationship. We say that something is equal to something else. Now, that equal sign tells us that this is an exact relationship. So please note, from a significant figures standpoint, these are all exact numbers, not measured numbers. Okay, so to give you an example of some equalities, we have 1 minute is equal to 60 seconds. Okay, so that's an example of an equality. 1 minute is the same thing as 60 seconds, or you could say that backwards. 60 seconds is equal to 1 minute, right? 60 seconds is a minute. It doesn't matter which way you write an equality, right? Both sides are equal. Okay. Now, what do I do with these equalities? Well, a conversion factor takes an equality and expresses it as a fraction. Now, if you multiply a number by this fraction, you're going to convert it into the other unit in that equality. I'll show you some examples so you can see what I'm talking about. But that's essentially how you do it. Now, with any fraction, you can write it one of two ways. Okay, so if you have the 2 halves of your equality, one number can be your numerator and the other can be the denominator. But you can flip that and you can still have that written the other way. So to put this very generically, if we have an equality where A is equal to B, we can write out our conversion factors as either A over B, or we can write it out as B over A. Okay, those are the 2 conversion factors we would get from that equality. Okay, and again, this is just the nature of these equalities. To use my number earlier, or my example earlier, where 1 minute is equal to 60 seconds, you can write that either way. You could say 60 seconds is equal to 1 minute, and you'd still be saying the same thing. Likewise, you could write that out as a fraction, 60 seconds per every 1 minute, or 1 minute per every 60 seconds. That relationship is still true due to that equality being true. Okay? Which one do we select, though, right? If we're going to multiply a conversion factor by a quantity, how do we determine which one of these 2 fractions we're going to use? To do that, we need to see what we're starting from. Okay. Before I do that, before I do some examples of using conversion factors, let's look at how to get conversion factors from various scenarios. Be careful of times when you've got units that have multiple smaller units in them. For example, if you're told that you've got a speed of 85 kilometers per hour, that's the same thing as saying that the motorcycle here is traveling 1 hour when it covers 85 kilometers, or 85 kilometers for every 1 hour it drives. So notice that we can treat this as an equality where 85 kilometers, when we see 85 kilometers per hour, that's the same thing as saying that for this motorcycle, 85 kilometers is equal to 1 hour. Okay? And then we can write that as 1 hour per 85 kilometers or 85 kilometers per 1 hour. These are the two conversion factors we get from this equality. Likewise, if we have one tablet is equal to 500 milligrams of vitamin C, we could write that as one tablet per 500 milligrams or 500 milligrams per one tablet. Now, if you get a percentage, the term percent means out of 100. So whenever you get a percentage, just realize that it is whatever number out of 100 of whatever it is a percentage of. So for example, let's say you're told that a particular food item contains 18% of fat. Okay, it's 18% fat by mass. So that means that if you had 100 grams of food, that 18 grams of those 100 grams comes from fat. Okay, so if I see a percentage here, I know that that's 18 out of 100 of something else. So this is 18% of fat out of the total food. So the total food is 100. Okay. Now, what you use for your units is totally up to you. You could say there's 18 grams per 100 grams of food, 18 grams of fat per 100 grams of food, or you could say there's 18 ounces of fat per 100 ounces of food. There's 18 kilograms of fat per 100 kilograms of food, and so on. My point here is that that relationship of 18 to 100, or 100 to 18, depending on how you flip it, comes from that percentage. Okay, that percent is where we're getting that 100 from. The cent in percent is 100. This is not going to be as important for this class, but for those of you who do go on to biology type classes, when you start dealing with really low concentrations in parts per million and parts per billion, those are basically like percent, but instead of being out of 100, they're out of a million or out of a billion. Now, to make those numbers a little bit easier to deal with, you can scale things up and down accordingly. So for example, if we're dealing with parts per million, instead of dealing with grams and grams, I could use milligrams and kilograms, and there's a difference there of a million, right? There's a million milligrams in 1 kilogram. So saying 2 parts per million, it's a little bit easier to deal with that if I use milligrams and kilograms. Again, don't stress about this. We don't really have to worry about that for this class. But for those of you who are going on to other classes where you do see ppm and ppb a little bit more often, just realize it's the same concept as percent. Okay, it's just scaled up. Okay, so with that in mind, how do we solve problems using conversion factors to, well, convert things, right? This is one of the key skills you're going to pick out of this course. Okay, so using conversion factors, being able to convert from one unit to another, that's a concept we call, or a skill we call, dimensional analysis. It's a really useful skill. I'd say if you were to get this is probably the most useful thing you're eventually going to get out of this course, because it really applies to pretty much any other kind of quantitative reasoning. Whenever you're doing some sort of conversion, if you're keeping track of your units and knowing where you multiply and where you divide, that's really all the work done for you. You can be really confident in your answers if you just keep track of your units. Okay, and I'll show you how to do that. Don't panic if this is the first time you're doing this and it seems a little weird because you haven't seen this before. We're going to be practicing this throughout the year or throughout the semester, and you're going to get better at it. Okay, so don't panic. just because you're not good at it immediately, this is again one of those things where different people have different learning curves on this. Okay, you will get better at this. Don't get frustrated if it takes you a little bit longer than you'd like. Okay, now the other thing that's also going to be useful here is that notice that here in this problem we have a paragraph that's written and there's not a single number or like digit written there. Everything's in words. And I think that's another thing that students find frustrating. How do you look at a paragraph, all right, a whole bunch of words written out, and get meaning out of them? Figure out, what is the question asking me? What am I supposed to do with this text, right? This is the other useful skill you're going to get out of this class. And again, there's a little bit of a learning curve to this, so don't get too frustrated. You will get better at this as we go along, okay? So what I like to do when I started learning how to do this, what really helped me was reading this and then underlining the key words, the numbers in the problem. Okay, so especially in a problem like this where none of the numbers are written out using numerals, they're all written out as words, I'm going to read this out loud and ask myself, where are the numbers in this? And I'm going to underline not only the numbers themselves, but also the units tied in, because that's going to help me with that dimensional analysis. So let's have a look through this problem. The average person in the US consumes 1/2 pound of sugar per day. How many pounds of sugar would be consumed in 1 year? So let's read that again, but looking at the numbers associated with this. The average person in the US consumes 1/2 pound of sugar per day. Okay, so notice that 1/2 is a number, and pounds of sugar per day, those are units we're probably going to pay attention to. How many pounds of sugar would be consumed in 1 year? Okay, so I've underlined the numbers there. Now, the other thing that's really important that doesn't have a number tied in, but is important to identify in this problem, is what is the question asking me? And you'll usually have a question word like how or what or things like that in the question. And so, or which I think is another word you'll sometimes see. So here, that question word is the word how many, right? So what is the question asking us for? It's asking us for pounds of sugar. How many pounds of sugar? So we've got the starting point of the problem, right? So the question's asking us about pounds of sugar. It's starting us with 1 year. It's asking, if we started off with 1 year, how many pounds of sugar is that equivalent to? Now, there might not be a direct way to connect years and pounds of sugar, but hopefully we can get enough conversion factors involved between either what's given in the question and what we know from our own knowledge to come up with some sort of game plan for solving this problem. So first things first, start out by laying out the problem. What is the question starting you with? I mentioned that the starting point is 1 year. It's in the same part of the sentence that's tied into how many pounds of sugar. The final quantity, of course, is pounds of sugar. That's what the question is asking us for. How many pounds of sugar? So we know that that's where we want to wind up, with pounds of sugar. How do we get from 1 year to pounds of sugar? Well, we're going to pick conversion factors that cancel out the units from, in a previous step and push us towards units in the next step. Okay, so hopefully by canceling out units that way, we'll eventually be left with pounds. Okay, so in this case, we're starting off with 1 year. Okay, and we want to get to pounds. Now, something that might give this away is that the word day is involved in the units of something given earlier in the problem. And we do know out of our general knowledge that years can be connected to days, right? And of course, now we can also see that we've got pounds of sugar per day, so we know that we have a way to connect pounds of sugar with days. Okay, so that's going to be our game plan. We're going to go from years to days to pounds. Now, how do we do that? Let's write out our conversion factors. Okay, so let's look at the equalities from this question. We know that 365 days is equal to 1 year, and the question told us that there's a 1/2 pound of sugar for every day that Americans consume. So if those are our equalities, let's write those out as conversion factors. Now we see that that's where these equalities belong, right? So 365 days and 1 year, we're going to use that to go from years to days. And likewise, we can go from days to pounds by knowing that 1 day involves half a pound of sugar. So the conversion factors, remember, you take an equality and you write the two fractions that this produces, right? So 1 year is equal to 365 days. You could say there's 365 days per every year, or there's 1 year for every 365 days. Likewise, for half a pound of sugar is equal to 1 year, you could write that out, 1 day, my bad. You could say that there's half a pound of sugar per day, or 1 day per half a pound of sugar. So, which of these conversion factors are we going to use in our problem? Well, we're starting off with 1 year, right? So, we want years to cancel out. Now, to get a fraction to cancel out, or to get units to cancel out, you want it to be the numerator in one step and the denominator in the next step, because anything divided by itself will cancel out, right? If you write a fraction where the numerator and the denominator are the same number, they cancel out and leave 1. So for example, 2 divided by 2 is 1. That's why 2 halves make a whole. Okay? It's the same thing with units. If we start off with years, we want to pick a conversion factor that has years in the denominator. So which one is that? So out of these two conversion factors that have years in them, which one has years on the bottom? Okay, it's going to be this one, 365 days per 1 year. So we write that conversion factor, and we know that years will cancel out that way, because we've got years being divided by years. Okay, well, that leaves us with days. So now we have the same problem again. We want days to cancel out, because we want to get to pounds of sugar. Okay, and we know that days isn't there in the units of the answer. So, which conversion factor do we pick that cancels out days? The conversion factor on the left has days on the denominator, so we write that out, and we see that that also cancels out days. Now notice that we have pounds of sugar left. And guess what? That's what we want, right? So that's how we know that we've set up our problem correctly. If pounds of sugar winds up in the numerator, that tells you you've set this up correctly. So how do we get the numerical answer for this problem? Well, 1 year times 365 days times half a pound of sugar gives us 182.5, which I've rounded off to 183 here. It's technically not the right number of sig figs, but we're going to ignore sig figs for now, just in the interest of simplicity. There are no numbers written here, but again, you can assume that's 1. So we're dividing by 1 and we're dividing by 1, which is the same number. Okay, so anything that's on the denominator is a number you're dividing by. Anything that's on the numerator, you're multiplying by. Okay, and that's how you kind of set this up once you have, once you've plugged in your conversion factors. That's how you figure out the numbers. So it's going to be 1 times 365 times 0.5 divided by 1 and divided by 1. That's how we get that answer there. Okay. Now, a quick note here about how I've set up this problem. This sort of table I've made, where I've plugged in my conversion factors as columns in the table, that's one method to set this up. And I like this one just because I think a lot of students probably saw this method or something similar in high school. You do not need to use this if you learned a different method in high school for canceling out units. For example, when I was a student, what we would actually do was write down the conversion factors one after the other. Instead of doing these all in one line, we would do each of these step by step. I would first convert years to days by multiplying by 365. Then I would take that answer and I would multiply by pounds of sugar per day to get my answer in pounds of sugar. Okay, I would do that in 2 separate steps on 2 different lines of my calculation. Some people might like to use ratios to set up their multiplication and division. It all depends on what you're comfortable with. And to be honest with you, the math will wind up being the same. You're still going to multiply and divide the same way. Your units will still cancel out the same way, even if you've learned a different method for bookkeeping those units. Okay, so don't stress out if the method I'm showing you with this table is a little bit different from what you may have seen in a science class in high school, okay, or in a different science class that's not this one. Um, Whichever method you like can work. And I've seen pretty much every method there is. So if we are working on a problem together and you want to use your other method, I'll be able to follow along and help you with it. Okay, so don't stress about that. Yeah, but that being said, I do like this table method because everything's on one line and it's easy to kind of follow that flow of where those units are canceling out. Okay, so that's kind of it when it comes to dimensional analysis. Always be ready to, when you're reading your problem, I recommend like reading through it and underlining the numbers and the units attached to them. Okay, so look for any numbers, underline them along with their units, and then ask yourself, what is the question asking me for? And what is it giving me as the starting point for that problem? So again, look for like a question word like how or which or when, and look for what quantity is coming after that. And that's what you want to wind up with all the way on the right of your calculation. Okay? And then whatever it's starting you from in that, usually in that same sentence, that's all the way on the left of the problem. Okay, then we select equalities and convert them, make them conversion factors, and then plug in the conversion factors so that our units cancel out in each step until we're finally left with the units of the answer we want. And then you just treat the numbers. You just multiply all the things on the numerator, divide by all the things on the denominator, and what you get numerically is your answer. And that's it. And that, like I said, once you figure out that skill, that's like 90% of the math you'll see in this class. So again, don't panic if it takes you a little while. You're going to get better at it. By the time we get to the final, you'll be great at it. But the sooner you get the hang of it, the easier you'll find this class. Okay. So the last topic I'm going to end on in this chapter is density. Okay, so we're going to talk about a quantity called density, or a thing that we can measure, a property, I guess, that we can measure. And we'll spend an entire lab playing around with this. So the lab next week, or our second week of classes, will be on density here. What is density, right? Density is a relationship between mass and volume. So it kind of tells you how tightly packed matter is, how fluffy something is, so to speak. Okay, the units for density involve the units for mass and volume. Just like the units for speed involve distance and time, like miles per hour, right? Miles are a unit of distance, hour is a unit of time. In the same way, the units for density involve units for mass, usually grams, and units for volume, usually milliliters. Okay, now you'll see some variations of this. Sometimes you'll see cubic centimeters instead of milliliters, but remember, cubic centimeters and milliliters are basically the same thing. So if you see a unit of grams per cubic centimeter, realize it's the same thing as grams per milliliter. Okay. Gases have very, very low densities. That's why gases tend to rise in whatever medium they're in. And so because they have such a low density, it usually makes more sense to describe their density in terms of grams per liter rather than milliliters. So generally speaking, gases are the least dense compared to solids and liquids when it comes to materials. Solids and liquids have about, they're both significantly more dense than gases, and they're about the same density. Liquids tend to be a little bit less dense than solids, though there are a few weird exceptions here and there. So for example, like one of the weird exceptions is ice. Due to the way the ice crystals pack, ice just happens to be less dense than liquid water. So it's one of the weird things where ice floats on liquid water, whereas most solid materials will sink in a liquid of the same type. All right. Anyway, how do we calculate density? So density is just mass divided by volume for a particular object or a particular material or sample of material. Now, you could memorize that, but to be honest with you, you could just figure that out from the units of density. Density is grams per milliliter, right? Grams is a unit of mass, milliliters is a unit of volume, so it's literally the mass divided by the volume. So, how do we do that experimentally? And again, we'll see a lab where we kind of practice this, but to get the mass of an object, that's pretty straightforward. You just put it on a scale and see what the mass is in grams. Volume can be easy or difficult depending on the type of object you've got. If you have a very regularly shaped object, so let's say something that's a cube or cylinder, you can calculate the volume of that object just using regular geometry. If you've got an irregularly shaped object, okay, and to be honest with you, you could do this with a regularly shaped one as well. It's just, in the case of irregular objects, you really have to do this method because there's no geometry formula that covers it. To get the volume of something irregularly shaped, you can figure it out through displacement. So if you have a sample of water and you know its volume, and you add in your object and you see what the volume rises to, that difference in volume, that volume of water that's displaced, is the volume of your object because your object had to displace that water. So here's an example. So let's say here we have a graduated cylinder with a volume of 35 milliliters or 35.5 milliliters. We add in this object and the volume rises to 45 milliliters. Well, what's the difference in volume there? Well, that's a difference of 9.5 milliliters. So that tells us that our object must have a volume of 9.5 milliliters. That's what caused the volume to go up by 9.5. Okay, so because density involves mass and volume, it can be used as a conversion between those two things, right? So it can also be used to identify a lot of materials. Oftentimes materials will have a very specific density, and so you can identify a material by figuring out its density there. That being said, you do not need to memorize densities. If you do need a density of a material to solve a problem, the problem will, on a quiz or exam, will give you the density, right? You won't be expected to memorize it. The only material where you do have to memorize the density is water. Water has a density of 1 gram per milliliter at room temperature. Okay, now that's an easy number to remember, right? 1 gram per milliliter. This is why, by the way, water is used to standardize so many things in metric units. Okay, it also makes conversions with water really, really easy because since it's 1 gram per milliliter, whatever your mass is in grams is going to be the same as the volume in milliliters. So if you have 15 grams of water, its volume will also be 15 milliliters. Okay, so something it's good to keep in mind. Okay, let's try some practice problems that involve density calculations. So let's say we have 48 grams of a metal. Oh, actually, so let's practice reading this the same way I taught you earlier about getting useful information about this. So if I'm reading this problem, okay, and I say, what is the density of 48 grams? Okay, so there's a number with a unit. That's kind of important. 48 grams of a metal if the level of water in a graduated cylinder rises from 25 milliliters to 33 milliliters after the metal is added. So the question's asking me, what is the density? Okay, so I need an answer of density in grams per cubic centimeters. Okay, that's where I eventually want to wind up. So what is the question starting me with? Well, it's giving me grams, and it's giving me volume. But instead of giving me the volume of the object, of the metal, it's giving me the volume of water. So how do I figure out the volume of my metal object? So we've got to work kind of backwards here a little bit first. So try and visualize what's going on here. We started off with a graduated cylinder with 25 milliliters of water. We added in our object, and it went up to 33 milliliters. So what is the volume of the object? That's not the final answer, but we know that we are going to need volume to figure out our density eventually. So what's the difference between 33 and 25? That is a difference of 8 milliliters. So our object had a volume of 8 milliliters. It had a mass of 48 grams. Now, since we know that our density is grams divided by milliliters, or mass divided by volume, we would take those two numbers and write them out accordingly. So we take our 48 grams, divide by 8 cubic centimeters, or 8 milliliters, and we get 6 grams per cubic centimeters. Again, the units make sense because we're taking grams and dividing by cubic centimeters, so our answer has to be in grams per cubic centimeters, which is, of course, the units of the answer we wanted, so we know it's correct. Now, since density has both mass and volume in it, it can be treated as an equality. So it's the number of grams for every 1 milliliter of substance. So, for example, if you have something with a density of 3.8 grams per milliliter, that's saying 3.8 grams is equal to 1 milliliter of that material. Okay, so like before, you can write two conversion factors from this. You could say there's 3.8 grams per 1 milliliter, or if we flip that, there's 1 milliliter per 3.8 grams. Which of these conversion factors you use depends on what you're starting from and what you want to end with. Okay, are you going from grams to milliliters or from milliliters into grams? So let's try a practice problem with that. The density of octane, a component of gasoline, is 0.702 grams per milliliter. Okay, again, notice the number in that, right? That's probably something that's going to be important to hold on to there. Okay, what is the mass in kilograms? Again, notice the question, what? So we want the mass in kilograms, right? That's what we're trying to find out. And what is the mass of 875 milliliters of octane? That's the material we're using. So we are starting with 875 milliliters, and we want to wind up with the mass in kilograms. Okay? So think about how you would set this up, and then how would you use your conversion factors to convert accordingly? Okay, so feel free to pause this video if you want to have some more time to think about this. But we have 875 milliliters. We want to convert to mass, right? Now, 0.702 grams per milliliter is the same thing as 0.702 grams per 1 milliliter, or if you flip that, 1 milliliter per 0.702 grams. So let's write out those two conversion factors, right? We could write that as either of these two fractions. Okay. Now, which one do I pick? My starting point was 875 milliliters. So I know that I want to pick a conversion factor that gets milliliters to cancel out, so I'm going to pick the conversion factor on the left, 0.702 grams on the top there, divided by 1 milliliter. And that gets milliliters to cancel out. Now, if you were doing this problem and you stopped here, you probably missed where the question wants the answer in kilograms, not grams. There's one more step here. We've got grams. The question wants us to convert into kilograms. So you have to memorize what does the prefix kilo mean, what does it mean, and 1 kilogram is 1,000 grams. So there's 1 kilogram for every 1,000 grams. Just as there is 1,000 grams for every 1 kilogram, right? We've got two conversion factors there. So again, which one do we pick? Well, we had grams left behind in the previous step, right? So we want that to cancel out, so we pick the one with grams on the bottom. So that's why it's 1 kilogram per 1,000 grams. Okay, let's plug those numbers in and see what our answer is going to be in kilograms. We would take 875 times 0.702 times 1. and we divide it by 1 and, and divide by 1,000. So the answer you get is 0.614 kilograms. Okay. Here's another practice problem for you to try out. I'll let you try it out yourselves, but I'll kind of narrate it really quickly. So feel free to pause this video if you want to have more time to practice it. Okay. So in this problem, we have the question's giving us the density of iron. Oops. So we've got a density of iron is 7.87 grams per cubic centimeter. We are told that we have 52.4 grams of iron, and we're adding it to 75 milliliters of water in a graduated cylinder. Now notice that's water, not iron. Okay. To what volume will the water level rise? Okay. So if you're having trouble visualizing this, basically we're starting off with our metal object. We start off with a graduated cylinder where the volume reading is 75 milliliters. We put in our metal object. Okay, that's going to go into our graduated cylinder, and our water level rises. What is the new volume? Right? So the difference in volume here, so the difference in volume here is going to be the volume of this object. Okay, so this volume is what's going in there. So your first step is probably to figure out that volume. So you've got the mass, that's your starting point. You've got the density. Figure out, how am I going to convert that into milliliters or cubic centimeters? Do I multiply by 7.87 or do I divide by 7.87? What would get grams to cancel out? Okay. So there's more than one way to do this. You could either take the density formula. If you know that density is mass over volume, you could rearrange that so that volume is mass over density. Or you could do it setting up a table like I have. So 52.4 grams of iron, you would divide by the density, and that gets grams to cancel out and be left with only milliliters. Okay, so you have 6.658 milliliters of iron. Okay, you could have figured that out also, just like I said, if you like algebra and you like rearranging formulas, you just say, all right, if my volume is mass over density, I've got a mass of 52.4 grams of iron. I'm dividing by my density of 7.87 grams per milliliter, and that's going to give me my volume of iron accordingly. Okay. Now, again, that's not the end of the problem, right? The question didn't want the volume of iron, it wanted the new volume of the water. And we know that the new volume of the water is going to be the old volume added to the volume of the iron that's been dumped in there. So when we do that, we should get 81.7 milliliters. Okay, so that's how you would approach a problem like that. Again, we do a lab on density, so you get to play around with these concepts a little bit more, but that's essentially like how we can use density or how we can do conversions involving density. The other useful thing with density is it gives us an idea of the buoyancy of the materials we're dealing with. So if we compare the density of one object and another, the one with the lighter density will float in the heavier one. Likewise, if you have a heavier or more dense object in a medium that's less dense than it, that object will sink. Okay, so here we can see a bunch of materials in liquid water. Liquid water has a density of 1 gram per milliliter. So you can see that the items that have densities lower than that are floating, and the items that have densities higher than that are sinking to the bottom. Okay, so with that in mind, we can use density to sort out what things are floating and what things are sinking. So here we have caro syrup, vegetable oil, and water, and all three of them have different densities. We have caro syrup with a higher density of 1.4 grams per milliliter, vegetable oil with a lower density of 0.91, and water, of course, is 1 gram per milliliter. Okay, so since we have a number that's higher than that and a number that's lower than that, let's use water as our central point. Okay, so ask yourself which one will have, will be floating above our water, which one will be floating or will be sinking. Which one will be floating above the water, which one will be sinking below the water. Though looking at your answer choices, it should be pretty clear that the answer is going to be the first one, right? Since water is the this option is the only one with water in the middle, and water is the middle of these three numbers. It has to be option number 1. But if you want to confirm that answer, you can see your vegetable oil with its lower density is floating on top. Your Caro syrup with its higher density is sunk to the bottom. Okay, now in your lab, you may come across the term specific gravity. And if you're wondering what that is, if any of you have ever brewed beer, you've probably heard of that term as well. And you've probably used a hydrometer. If you haven't, no big deal. It's in the video that I've recorded for our second lab. Not beer, but use of a hydrometer to determine specific gravity. Okay, but what is specific gravity, right? Specific gravity is just the density of a liquid compared to the density of water. So you're going to take your density of your liquid and divide by the density of water, which is 1 gram per milliliter. Well, any number divided by 1 is still the same number, right? So your specific gravity is numerically going to be the same as your density. Okay, so that's the nice thing about specific gravity, or rather a silly thing about it, but they're going to be the same number. The only difference, though, is because you're taking the density of one material and dividing by the density of another, the units cancel out. So specific gravity is actually unitless. It's just a number. So it's one of those rare measurements that doesn't have a unit following it. Okay. So so that's basically all you'd have to do to figure out specific gravity. You just take the density of your material and divide it by the density of water, which is 1 gram per milliliter. So it's just the same as the density. And that's it for this chapter. We have finished our first chapter. So I've included some practice problems here I recommend you try. So go ahead and try those out from your textbook. Again, if you run out of problems, if you've done a few problems and you're like, I wish I could do some more practice, try looking at nearby problems in that section. If you have any questions on those, feel free to come to me in office hours. I can work through some problems with you. And if not, I can also direct you to some other resources to look for extra problems if need be. Okay, so have a good day.